Let me know if I'm audible. Good evening, Ravi Ashwin. So I hope I'm audible, right? Okay. So Somit Sinha is saying that please don't give the example of Fibonacci series. It's irritating. Sure. I'll keep the Fibonacci series aloof. Okay. So let me share what I have planned for the recursion. So let me share the screen with you. Okay. And okay. So this is what plan looks like. And okay. So we have a lot of comments. Yeah, I get it. I'm audible. Okay. So now let's move ahead. So first I decide, I had this notion that where should I start my recursion from? So I decided that I would start recursion from the very basics so that I can take as many people as along with me in this journey of recursion. So I'll start from the very basics. The only prerequisite that we would have is that you should know what function calling mechanism is and what functions are. So something around that. So you should know that. And apart from that, we would start from mathematics behind recursion. We would start from analogy with the mathematics, and then we'll start with very basic recursive functions, and those will be void recursive functions, and we'll start with having some insights around them. Then we'll go into non-void recursive functions. Non-void recursive functions with single recursive calls and some insights around them. Then this is my favorite question, the Tower of Hanoi question. All the insights that we have generated so far will apply, and we will apply it into Tower of Hanoi, and we'll see if we can solve that or not. And then I would like to move to the variations. The recursive function in strings generally have two variations, get and print variation. So I would like to move to that variation as well. So these are probably these three topics are in my agenda. So let's see how many we are able to actually tackle and how many we are able to learn during the whole webinar. So let's start. Okay. So let's start with the very basics. So somebody asked me what is PMI and how do you relate with recursion? Okay, so right. So as we all know that if I talk about something like f of x equal to, let's suppose 2x plus 5, right? So this is a function in mathematics. We have something related to it in programming as well. We have functions. So if I see this thing, so I can relate it to programming as well. Analogous to it, we have functions in programming. So a function in programming related to it would look something like this, right? Would look something like this, 2 into x plus 5, right? So similarly, recursion is also analogous to something in mathematics, right? So there is a concept called PMI. So let me talk about PMI. Let me quickly revise PMI. It was the 4th chapter of mathematics in class 11. And if you have done it properly, or if you haven't done it properly, we will just quickly brush up. So what PMI is, PMI stands for Principle of Mathematical Induction. And it is used to verify all the formulas, all the expressions that we have. So let's take a generic expression. A generic expression, sum of first n natural numbers. Sum of first n natural numbers. So sum of first n natural numbers is basically equivalent to n into n plus 1 divided by 2, right? So this is n into n plus 1 divided by 2, right? We all agree with this. But PMI is used to verify it. PMI is used to define whether it is correct or not. So what PMI does is, there are simple steps in PMI. So the first step is we assume that it is true. We assume that it is true without even basically starting with anything. We just basically say that let's take a natural number. Let's take a natural number. Let's say n equal to 1. So if n is equal to 1, the left hand side of this expression becomes 1, and the right hand side of this expression becomes equal to 1 into 1 plus 1 divided by 2. So this would be equal to 1. So for n equal to 1, this is true, right? We agree that for n equal to 1, this is true. So then what we do is, without doing anything, we assume that this expression, since it holds valid for n equal to 1, we assume that it would be valid for any generic n equal to k. So we just assume, this is the assume step. This is the assume step. So this expression would become something like this. So on and so forth, and here it would be k. And the left hand side would become k into k plus 1 divided by 2. So after assuming this, what we have to do is we move to two-proof step. We move to two-proof step. And what is this two-proof step? So in two-proof step, I go to p of k plus 1. And in p of k plus 1, what I do is I write this expression, so on and so forth, till k plus 1. And I have to prove that this is true. Now you would say, assuming this is true, I have to prove that this is true. So for that, what I have to do is I have to make left hand side equal to right hand side. So assuming that the first expression is true, this much part can be replaced by k into k plus 1 divided by 2. I hope this is comfortable with you, right? And then basically there is k plus 1 over here. Then what I can do is I can take k plus 1 common out of it, and I'll get k by 2 plus 1, right? And this would be equal to k plus 1, and then this would be multiplied by k plus 2 divided by 2, right? So this is how my left hand side has been transformed into right hand side. This is now equivalent to right hand side. So what I can say is that assuming that p of k is true, I have proved that p of k plus 1 is true. And after that, what we do in PMI, we just say that since p of 1 is true, and since p of k is true, and from p of k, since I can prove that p of k plus 1 is true, I can say that it is true for all natural numbers. How that is relevant, how this is true, right? So this is true because if p of k makes p of k plus 1 true, so I can make from p of 1, I can make p of 2 as true, and from p of 2 I can make p of 3 as true, so on and so forth, right? Since k makes k plus 1 as true, so 1 can make 2 as true, 2 can make 3 as true, 3 can make 4 as true, so on and so forth. I can prove that this expression holds true for all natural numbers. So this is what PMI does, and PMI has simple 3 steps. It has something called trivial case, and something called assume step, and something called true proof step, right? Let's quickly analyze it and basically map it to recursion. So what recursion does is recursion, let's solve this problem, sum of n natural numbers through recursion. Let's solve this problem of sum of n natural numbers through recursion. So you have to write a recursive function. Let me give you a brief overview, a brief structure of how I want this to be done. So let's suppose this is the function. You would be provided n over here. And let's suppose if n is equal to 5, so I want you to print the sum of first 5 n natural numbers, which is 1, 2, 3, 4, and 5, which must be equal to 120. Now this is something that you have to do. So this is the problem that I have in my hand. So this is exactly mapped to the two proof step. So the expectation that I have from my function is that, so this two proof step is my problem. So my problem, or the expectation that I have from my function, is that if I have been given n, then I have to print sum of first n natural numbers. I have to print sum of first n natural numbers. Now, analogous to the assume step, I have some step which is called subproblem, or let's suppose I'll name it as faith. So I would say that f of n minus 1, I would just assume that it works for a smaller step. So I would just assume that if somebody has asked me that find the sum of first n natural numbers, then I'll just assume that the sum of the first n minus 1 natural numbers would automatically come to me. So if somebody has still told me that find the sum of first five natural numbers, I would assume that the sum of first four natural numbers will come natural to me. I'll assume, I'll have that faith, and basically I'll get the answer for this faith. This answer would be equal to 24. If f of 4 is equal, if n equal to 4, then this would be equal to 24. Now the third step that we have to do is we have to solve the main problem. We have to find the expectation using this faith. So if I have the answer of f of n minus 1, if I have the answer of f of 4, how do I find the answer of f of n? Simple, isn't it? Just I have to add 5 to 24, right? I just did a small mistake. I was trying to multiply everything. I was basically finding factorial, right? So this is a small mistake that I have done. So this should be 15. Sum of first five natural number is 15, right? And similarly, so here, sum of first four natural numbers would be equivalent to 10, right? So let me just quickly erase these things, right? Sorry for this part. Yeah. Okay. So yeah, right. I was talking about factorial, right? Okay. Right. A lot of comments around that. Yeah, I messed up around that. Okay. So I was talking about factorial at that point, but sum of n natural numbers for the first five numbers is 15. And if I talk about small answer, if I talk about small sub problem, if I talk about my faith, so f of 4 would be equal to 10 because 1 plus 2 plus 3 plus 4 is equal to 10, right? So I would assume that 10 would come to me. 10 would come to me naturally. So if 10 has been given to me, if my answer 10 has come to me, so what would be, how would I answer f of 5? It's simple, right? I just have to add 5 to it. This would be equal to 15 then. So this is what you have to do. You have to first see and you have to create an expectation over your function. The expectation is your problem itself. You have to check what is your expectation or what your problem is. Then you have to make a faith. For me, the faith is f of n minus 1. You have to assume that the answer for the faith will come, right? You have to assume that the answer for the faith will come, right? So if my answer for the faith will come, then I have to figure out how can I express my expectation in terms of my faith, right? How can I find my expectation through faith? So this would be equal to n plus answer, right? So 5 plus 10 would be my answer. So after that, after doing this, we will basically write high level code. So this is something that we will do after it. So if I write high level code right now, so my high level code will approximately look something like this, right? It would look something like this. So this is the problem that I have, and my sub problem would be equal to f of n minus 1, which would be equal to int answer, right? And if this comes out correctly, then basically what I can return is, how can I find the answer to my problem? My answer to the problem would be n plus answer. So this is my high level code. So you have to come to this high level code. You have to assume an expectation. You have to see what your problem is. Then you have to have a faith. You have to have faith, right? You have to have faith that what would your answer will be. So you have to assume that your answer will come. And then you have to just add and find how you can find the answer from your faith. How can you find your expectation from faith, right? So that's how you will find, right? But the problem to this is that this, if you run this code, it will give you infinite recursion. Because recursion works similarly like function calling, right? So how function calling works is, so now we will try to execute it on stack frame. So after that, we will execute it into stack frame. And for stack frame, what we have to do is we have to do low level analysis. So this is now infinite recursion. To this point, it is infinite recursion because it will continuously recursively call itself. So to stop that recursion, we have to make a base call. So for what we have to do is we have to just see that how it will basically apply itself on stack frame, right? So as I said, right, so we should have a facts clear, we should have a basics clear of function calling mechanism, and we will use that over here. So let me quickly write that function for you. Let me quickly write that function for you. Okay, so now this would be return n plus answer. So this is high level code where we arrived right now. So now, from the main, the function calling mechanism starts from main. So the main calls f of 5. The value of n is 5, which is sent by the main. So here a layer of 5 comes, right? So my n equal to 5, n becomes equal to 5. So there are 2 lines of code. So the first line of code will be executed. And as the first line of call, as the first line is executed, what happens? It gives a recursive call to f of 4. So in the stack frame, another layer gets on top of it. F of 4 gets on top of it, right? So as we come over here, n is equal to 4 over here, and the first line gets executed. And as the first line gets executed, f of 3 gets on top of it, right? So the first line gets executed and n equal to 3, right? So the first line gets executed, another layer comes on top of it, and f of 2 comes over here, right? So the n is equal to 2 over here, and then the first line gets executed and f of 1 gets executed. Then first line gets executed, n is equal to 1 over here, and another layer of f of 0 gets at top of it, right? So I just want to tell you that I have reached up to function f of 0, right? And 0 is something which I don't want to add. I want to add 1 plus 2 plus 3 plus 4 plus 5. And even if I want to solve something where n is equal to 0, so what is the sum of first 0 natural numbers? Is equal to 0, right? So this is something where I want to stop. This is called base case. This is called base case. This is somewhere where I want to stop. So this is called base case. If I don't stop over here, so this is basically will go on and on and on. And this will basically go on and on and on. And stack frame will get overflow. So I get that I have to stop here. So I can write at the top of these 2 lines because I don't want to execute these 2 lines. So what I would do over here is I would basically write if n is double equal to 0, then just return 0. Because for n equal to 0, I don't want to execute the first line and I don't want to execute the second line, right? So this is something that I wanted to tell you, that what I'll do is for n equal to 0, I'll return 0. So it will basically return 0 from here. And what it will return, it will be caught by its below layer. So this will return and it will be caught by its below layer, and it will caught in answer. So in answer, it will catch 0. Then second line will get executed and it will return 0 plus 1. It will return 0 plus 1 to the below layer. Then basically it will add 1 and 2. So it will return 3 over here. Then what it'll do, it will add everything which is returned from the top layer and it will add 3 to it. So it will return 6 over here. Then what it will do, it will add 6 and 4 and it will add both of these values and it will return 10 over here. And then it will catch 10 from above. It will add 5 and it will return 15 to the main function. So sum of first 5 natural numbers comes out to 15. So this makes my complete function. So what I have done is I have done very simple things and I would like to map and analyze it to the PMI. So PMI had a trivial case. PMI had a trivial case. It had a assume step and it has a to prove step. We over here have an expectation step. Then we have a fate step. And then we write high level code by writing expectation in terms of faith. Then we write our high level code. After that, we dry run it to find the base case. Then we plug the base case. And then after plugging the base case, our low level code is complete, or you can say our recursion function is complete, right? So our low level code would be completed, and after our low level code is written, so then basically our whole function would be completed. This two proof step is mapped with expectation. This assumption step is mapped with faith, and this trivial case is mapped with base case. So this was what I wanted to map PMI with the recursion. So what I wanted now is I'll start with the next part. So this is something which I wanted to explain. PMI mapped to recursion. So let me go through the comment section if we can bring up some doubts. So if you have any doubts till now, so you can put it in the comment section. So otherwise, what I would like to do is I would like to move to the next step. Right. So like what Aman is saying is, Aman is asking what high level code is. So Aman, let me try and explain everything with more examples, right? So Bhavya Rana is saying something that as there is no task left after the recursive call, it will be easier for the compiler to optimize the code. When one function is called, its address is stored inside the stack. Okay. So these are few of the comments. Okay. So Janardhan Singh is saying there are no doubts, and Aman is again asking what high level code is. So now let me put it into more application, and let me put all the things that we have learned into more applications. So now first let's start with non-void functions. Or before that, now let's start with void functions. So before returning anything, let's first start with void functions. So let's suppose that you don't have to return anything. Aman, let me try and explain you in a way that you understand it, and I would basically create such recursive functions where you don't have to return anything, right? So let's start with something like this. So let's suppose you have to write a void function where you have to print something called print decreasing, and you are provided with something called int n, and you have to print everything in decreasing order, right? So if n is provided as 5 to you, what you have to do is you have to do simple one thing. You have to print everything in decreasing order. In the console, it should be 5, 4, 3, 2, and 1. You have to print it like this, right? So for this, I have to write a recursive function, right? So what I would do is I would do simple things. I would apply my same generalized approach. First, I would have an expectation. Expectation is nothing but it's the problem itself. So the problem is that you have to print everything in the decreasing order. If n is provided to you, if n is 5, then you have to print in console 5, 4, 3, 2, and 1, right? Similarly, now I have to assume a faith, right? I have to assume that for some smaller problem, it will automatically work. For some smaller problem, it will automatically work. I don't have to worry whether how it will work. I just have to assume that it will automatically work. So what I would say is, let's assume PD of n minus 1. So I would write PD of n minus 1. I would do a recursive call PD of n minus 1, and I would assume that it would work automatically. So if n is equal to 5, n minus 1 would be 4, and it will print in console 5, 4, 3, 2, 1. So this is something that I would assume, right? So for this, what I'll do, I'll just write over here PD of n minus 1. What would this line would do? This would do a simple thing. This would print 4, 3, 2, 1 in console. This would print 4, 3, 2, 1 in console, right? So this would print this on console. And what I want to do is, what is my expectation? My expectation is 5, 4, 3, 2, and 1. My expectation is 5, 4, 3, 2, and 1. What should I do? to basically convert this faith into my expectation. What should I do so that this basically gets converted into 5, 4, 3, 2, 1, right? There is a simple thing. I just have to print n over here. If I print n above it, then it will basically print everything like this, 5, 4, 3, 2, 1, and my problem would be solved. So this is my faith and expectation. My faith is that I will call on n minus 1 and I will just write print n, and my expectation would be solved. My problem would be solved. This is my sub problem, and this is my main problem that I want to solve. I just have to assume that my sub problem would get answered. I have to just make a recursive call on a smaller problem, But problem is that this is up till now an infinite recursion. So as you all know that to rectify the infinite recursion, what I have to do, I have to stop my recursion. So for stopping my recursion, what I have to do, I have to simply add a base case. So let's try to dry run. Let's try to dry run for a simple case. Let me quickly write my high level code over here. So this is my high level code. This is PD of n. Whenever you are dry running, you have to just assume a small case, and for that you have to dry run over a stack frame. You have to dry run for a small case, right? So this is something over here, right? So let's assume that my n is equal to 5. So in the starting, PD 5 would be called and the first line would be executed. As soon as the first line gets executed, let's say my console is over here. Let's say this is my console. Console is where I print something. Console is where I print everything and I put it over, right? So where I print everything. It's your screen. So as soon as the first line gets executed for PD5, 5 would be printed. Then as soon as the second line gets executed, PD4 would be called. First line gets executed, 4 would be printed. Second call gets executed, PD5 gets called. PD3 gets called, sorry. First line gets executed, 3 gets printed, right? And second line gets executed, PD2 gets called. First line gets executed and 2 gets printed. Then let me just put it like this. Then second line gets executed and PD of 1 would basically get called, right? So the first line gets executed and 1 gets printed. Second line gets executed and PD0 gets called. Now PD0 is something which I don't want to print. PD0 is something which I don't want to print. So I know that my n equal to 0 is my base case. This is where I want to stop my recursion. So I should write that for n equal to 0, I don't want to execute line 1 and I don't want to execute line 2. So what I would write is that if n is double equal to 0, I should directly return. This is something what I should do. Since this is void function, I don't have to return anything. I just would write return, void return. Since it is void, I'll just write return. And this will scrap off this function and I will get down. Now here it will try to execute the third line, but there is no third line. So this also gets scrapped off. So a function gets scrapped off from the stack frame if it finds a return or it finds the end of the function scope. So here, since it gets the end of the function scope, so it gets scrapped off. It gets down to PD2, and since there is also no third line, so it also gets scrapped off. It gets down to PD3, and there also, since there is no third line, it gets scrapped off. PD4 also gets scrapped off. PD5 also gets scrapped off, and we get to main function. And our console prints what was desired. So what was desired, we have to print everything in the decreasing order, 5, 4, 3, 2, 1. So this is my complete function. This is my complete function. So if n is double equal to 0, return, print the value of n and PD n minus 1. This is my recursive call, right? Just let me know if you have any comments. Just let me know if you have any comments. So I'll just quickly write void PD and int n. So if you have any question, just let me know. This is a brilliant thing that we were able to solve this question through just this expectation, faith, and base case, right? print n, and basically then you just have to make a recursive call print n minus 1, right? Right. So as I see that this function is clear to you, I don't see any question around this. So this is a recursive function, but this was a void recursive function. And the first thing that you have to understood is that we have, this is a single void recursive function. Single void recursive function. The insight that I wanted to deliver from this question is that you have to understand that in your recursive call, if this is your recursive call, let me change the color, or let it be this only. It looks good. White on black looks good. So if this is your recursive call, so there are two areas. This is area 1. Everything written over here is area 1. This is one insight that I wanted to share with you. Just listen carefully, that if you have a single recursive function, so your recursive call would be here. Everything above that recursive call would be executed in the above journey. So let's suppose this was your base case. And once you were going from the PD5 to the base case, this is very important insight that I wanted to share with you. Once you are going from PD5 to the base case, so whenever you are going from the PD5 to the base case, every time this area was getting executed, everything above PD of n minus 1, everything above the recursive call was getting executed. And after that, when you were coming back, then everything below this, everything in the area 2 was getting executed. Everything which was coming back, area 2 was getting executed. So you have two journeys. One when you are going upwards and one when you are going downwards. Another thing that I wanted to say was that local variables, the local variable is n, the local variables are initialized again and again. Here n was equal to 5, here the value of n is equal to 4. And here the value of n is equal to 3, right? So let me apply these insights to another question. So let's say this is, let's say you want to print increasing now. And let's suppose you have to print this function. Now let's say you have to print this thing, print increasing int n, right? And n is given to you. Let's suppose n is equal to 5, and you have to print this thing in console, 1, 2, 3, 4, and 5, right? So what you need to do is, you need to print this thing. So I have to assume a fate. So I would assume print increasing n minus 1. So what this would do is, if n is equal to 5, then print increasing n minus 1 would print 1, 2, 3, 4. If I want to print 1, 2, 3, 4, 5, and the I of n minus 1 would give me 1, 2, 3, 4. So for making 1, 2, 3, 4, 5, I just have to write 5 below it. So for that, what I have to do is, I just have to write print n over here. This is all that I have to do. And then, as you all know, that now this is high level code. So for terminating it, I have to put a base case. As I had done in the last question, the base case would be equal to n double equal to 0 return. If I could quickly dry run it, so this would look something like this. If I could quickly dry run it, so pi of 5, first this would be executed, n over here would be equal to 5. Try to see the two journeys. Over here, and try to see that local variables would be executed, would be initialized again and again. So n equal to 5, first line gets executed, and pi of 4 would be added. So here n would be equal to 4. First line gets executed, n would be equal to 3 here, and another layer of pi of 3 gets executed. 1 and this gets executed, n equal to 2. First line gets executed and n equal to 1 gets executed. First line gets executed, n equal to 0 gets executed. For n equal to 0, base case hits. So for that, we will come on the return journey. After coming on the return journey, we will print the local variable of local values of n. For here, we will print the value of 1 first. So in the console, I'll first print 1, then I'll come back and then I'll print the value 2 here. Then I'll come back to 3 and I'll print 3. Then I'll go over here and I'll print 4. Then I'll come over here and I'll print 5. So in the console, this function would print 1, 2, 3, 4, 5. Now we got that right. I just showed you how two journeys are possible and how local variables are being created again and again. How local variables are being created again and again, right? So as I can move to the comment section, I can see that a lot of people are saying that please move to a higher level, and it's just beating and let's beat further. So I would say that I think it's a pretty relevant insight which I've just shared, and I would like to move to the Tower of Hanoi, which is a better question and where you would appreciate all the insights that we have I have told so far or I have utilized so far, right? So before going to Tower of Hanoi, I just want to revisit the first question that I did. Revisit a similar question to the first question that I did. The first question I did was a non-void function. And non-void function means it would return something, right? And if I talk about something which returns, so let's talk about a function called factorial, whose example I mistakenly gave in the explanation when I was explaining principle of mathematical induction around sum of n natural numbers. So let's write a non-void function for factorial, right? Or let's do one thing, let's write power. So that would basically solve both the situations. It will basically solve both the problems. It will basically solve the problem of those people who want to learn a bit higher, and basically they want to learn something new, and basically those people also who are new to recursion. So this one is for them, right? So power function, there is a concept called binary exponentiation. So let's learn that. And this is a perfect example for learning something for those people who are starting just now, right? So let's talk about a non-void function where I would basically give two values, int x and int n, right? And the thing that I want to achieve from this function is that I want to return x to the power n, right? And let's suppose the value of 2, x is 2, and the value of n is 5. So 2 to the power 5, I want to return 32. Now let's see how you would be able to solve this question. We would exactly solve this question through the same concepts of expectation, faith, right? But the interesting part about this question is that this is a non-void function. But I would use a single recursive call. I won't use two recursive calls. For the two recursive calls, I would move to Tower of Hanoi, right? Which is far more interesting. For this part, I'll just stick to a single recursive call. So let's suppose somebody tells you that find 2 to the power 5, right? Somebody tells you that find 2 to the power 5, find x comma n. This is equivalent to finding 2 to the power 9. X is 2 and this is 5. So what I would do is I would have a faith. I would have a smaller problem. I would say that find the answer of this smaller problem. What would be that smaller problem be? I would say that find the answer of power of x minus 1. That find the answer of 2 to the power 4. It would return the answer of 2 to the power 4. Assume that it would return the answer of 2 to the power 4. Assume that it would return the answer of 2 to the power 4. So if this answer is returned, how would you be able to return the answer of 2 to the power 5? Right? So this would be equal to whatever answer I got from here, I would just multiply it with 2. Whatever answer I got it from here, just multiply it with x. So let me write it over here. So my answer would be equal to power x to the power of n minus 1. This is my faith. This is my faith. And I would extract its answer into this variable ans. And after I have got its answer in ans, what I would do is, to find the answer of the original problem, I would return x into answer. This would be my complete solution. This would be my complete solution, right? There is only one thing left, which is the base case, right? So we have to figure the base case. But you understand this thing, whenever you are trying to solve recursion, you have to just go down one step. You just have to go down one step, right? So now let's try to find the base case. For base case, what I'll do is I'll take a smaller case, and for the smaller case, I'll take the value of x to be 2 and the value of n to be 3. So I want the answer of 2 to the power 3. Now let's try run for a smaller case and let's find what the base case would be. So for the 2 to the power 3. So first step would be executed, and this would make call to 2, 2. First line would get executed, it will make call to 2, 1. First line would get executed and it would make call to 2, 0. Now 2, 0 I know about 2, 1 as well. So you can make either of the one as base case. So if I make this as base case, I would write that if n is double equal to 1, return x. I would say return x. Or if I want to make another thing as base case, if I want to make n equal to 0 as the base case, then I would say return 1. Because 2 to the power 0, we know that it would be equal to 1. Then this returns below 1. What would we do? We'll catch it and we'll multiply it with x, which is 2. 2 into 1, we will return 2. 2 into 2 will return 4. And 2 into 2 will return 8. This would be returned to main function. So this is how my function is. This is how my function is. This is my complete answer. But the problem with this answer is, that this is taking too much of time. This is making too much of time, because over here, what I am doing is, this is n. So let's suppose this is 3, then this gets down to 2, then this goes down to 1, then this gets down to 0. So it's going step by step. So what's the time complexity, if I could ask? So let's talk about interview problems. So you're asking interview problem. So let's say somebody asked you, so what's the time complexity of this recursive function? It would be order of n, right? So it would be order of n. So can we do better? So as I told earlier, let's talk about something called binary exponentiation. Let's talk about something called binary exponentiation. So binary exponentiation is something which will make it much more better, and it will make it much more relevant, and it will make much more optimized. And the complexity of binary exponentiation is order of log n. Shall we move to the order of log n? Do you have any doubts? Right? Do you have any questions up till this part? Should I move to binary exponentiation? Right? So let's move to the binary exponentiation. Let me explain you the binary exponentiation, and then basically I would come to the comment section again, right? Okay. So as we said, right? So for 2 to the power 3 or for 2 to the power 5, I had the faith that 2 to the power 2 would already be calculated. For the 2 to the power n, I had the expectation that 2 to the power n minus 1 would come automatically. For x to the power n, I had this faith that x to the power n minus 1 would automatically be calculated. Right. So this is something which I can optimize better. So I can say, let's suppose somebody asks me that find the answer of 2 to the power 5. So what I can say is that find the answer of 2 to the power 2. Find the answer of 2 to the power 2. So he would give me the answer of 2 to the power 2. It would be equal to 4. And then what I would do is, since it is odd, so I can say this can be equivalent to this 2 to the power 2 into 2 to the power 2 into 2. right? So I can say that if I have 5, I can break it down into half. So let's suppose somebody wants me to calculate 32, right? So somebody wants to calculate 2 to the power 5. So I can tell him that find 5 modulus 2, find 2 divided by 2. So it would be equal to 2 to the power 2. So I can say that since 5 is odd, then your answer would be equal to 4 into 4 into 2, or 2 into 2 into 2 to the power 2 into basically this, right? Or let's say somebody wants me to find the answer of 2 to the power 6. So I can say that find the answer of 2 to the power 3. If you find the answer of 2 to the power 3, then I'll basically, if its answer is ANS, so my answer would be answer into answer. If it is even, so my answer would be equal to answer into answer. If it is odd, my answer would be equal to answer into X, right? So this is how this question can also be solved. So let me quickly write the same function. So if this is given to me, so from the insight which I have just generated, I can say that find the answer of power x comma n by 2. Just see this part. I'm not saying that I'm not saying that do it n minus 1. I'm not saying make it n minus 2. I'm saying that find the answer of n by 2. So then I'll say that if n is odd, then return answer into x, and else return answer into answer. Right? My base case would be same. I'm not rendering it again. My base case would be same. If n is double equal to 0, if I get to a step where my n becomes equal to 0, so what I will do is I would just return 1. So now let's come to the part that how it is better. Let me describe you the time complexity of this function. So here what I can say is that if let's say we talk about 2 to the power 6. Now this is very fast. Earlier what we were doing is from 2 to the power 6, we were going to 2 to the power 5, then we were going to 2 to the power 4, then we were going to 2 to the power 3, then we were going to 2 to the power 2, so on and so forth. Right? Here what we are doing is from 2 to the power 6, we are directly going to 2 to the power 3. From here, we are directly going to 2 to the power 1. And from there, we are directly going to the 2 to the power 0. 2 to the power 0. From its answer, we are calculating its answer. From its answer, we are calculating its answer. And from here, we are calculating its answer. So the basic insight is that for calculating anything which is x to the power n, this is equal to x to the power n by 2 multiply by x to the power n by 2 if it's even, and if it is odd, it would be equal to x to the power n by 2 into x to the power n by 2 into x. So this is the basic insight behind it. And this is pretty fast. I am decreasing everything by half. So like in binary search, we go from n to n by 2 to n by 4, so on and so forth. So this is log n terms. Right? So the time complexity of this is log n. This function that I have just talked about, this is log n. Right? So this is way faster than what we have just talked about. Right? So now if you have any comments, now if you have any doubts, then just let me know in the comment section. I've just talked about two equations, two ways to go around it. One was the linear exponentiation, another was binary exponentiation. And Prince just told me that why to go for recursion then. So Prince, this is recursion, right? This is recursion. Recursion is similar to the fact that it is similar to iteration. It just has that extra overhead of calling itself, right? So it is similar. There are many problems which can only be solved by recursion, right? And there are many problems which can not be solved by iteration. So for those problems, we have to apply recursion. So by solving those problems which can be solved by iteration as well, we are understanding recursion. And then the recursion can be applied to bigger problems where we have to express choices. Like you all are saying that try to solve any n queens or try to solve a keypad problem. Those are problems which cannot be solved by iteration, right? And let's talk about Tower of Hanoi. Let's move to Tower of Hanoi. If you will all allow me to move to the Tower of Hanoi, it's one such question which you cannot solve by iteration. So, right. Tanuj saying is saying that please try to explain recursion with 2 or more recursive calls. I'll move to the part where Tower of Hanoi. In Tower of Hanoi, we have 2 or more recursive calls. So I'll move to that part. So apart from that, any more questions? Any more questions? Just let me know if you have any more questions. I cannot go from everything. Shrikant is saying explain binary exponentiation is in stack. Just go through and just try to make in the stack frame. I'll just give you a brief overview. For 2 to the power 6, if I would say, it will make call to 2 to the power 3 Shrikant. And then it will make call to 2 to the power 1 Shrikant, and then it will make call to 2 to the power 0. And this is how things go, right? Let's take an example of 8. So 2 to the power 8, it will move to 2 to the power 4, then it will move to 2 to the power 2, then 2 to the power 1, then 2 to the power 0. You see how it is going down by 2. Right? So, so this is how you can move everything, Shrikant. Move everything. You can go in stack frame and dry run it. So Anubhav is asking that try to solve Sudoku problem. Anubhav, there are a lot of Tower of Hanoi requests. So I would like to move to the Tower of Hanoi. It's much more relevant and it has 2 recursive calls. And we will apply our faith and expectation concepts. Aman is saying that, can you please explain the same expectation faith concept to solve 3 problems? So Tower of Hanoi is very much relevant for the 3 problems as well. So we will basically now move to Tower of Hanoi, and then we will basically apply our expectation and faith to it. And we can see that how the traversal is being done, how dry run is being done, and how everything is being done over here, right? So now let's move to Tower of Hanoi then. I hope up till now everything is clear to you. Okay. So now let's move to Tower of Hanoi then. I have the Tower of Hanoi question, and it's one of those questions which is taught in colleges, and it's very basic question. It's one of the classic questions, but it's not taught that well. So now let's try to do justice to this question. So let me first explain you the Tower of Hanoi, and here we will also test that whether those expectation and faith concepts that we have all used, whether it is true or not, whether they are as true as they look like, whether they can be applied to every problem or not. So let's try to apply them to Tower of Hanoi, right? So let me first explain you the question. You are given 3 towers. This is A, this is B, and this is C. Right? So in this ABC, we have n is equal to 3. Right? So we have 3 rods over here, and we have 3 discs over here. So the first disc is, you can say that the first disc is the biggest. And let's name the rods differently. So this is my source rod. This is my destination rod, and this is my helper rod, or you can see my auxiliary rod, right? So what I have to do is, let's suppose the biggest disk is A, the second disk is B, and let's suppose the smallest disk is C. And let's name the rods. This is 1, this is 2, and this is 3. Right? So something of this sort, right? So what you have to do is, you have to move all those 3 disks. You have to move all those 3 disks, A, B, and C, from the source to destination, making use of helper. But there are 2 rules. You have to listen those rules really carefully. The first rule is that you can put only small disk over a bigger disk. So smaller disk can only be kept over a bigger disk. You have to have a bigger disk below it. You cannot put the smallest disk C below down, and you cannot put B over it. You have to put bigger disk below and a smaller disk above, right? So apart from that, the second thing that you have to is you can take only one disk at a time, one disk at a time, right? So these are the two rules. These are the two rules that we have to follow, right? Now we have to see what the faith is, what the expectation is. Now let's first try to write the function. Let's first write the problem. So let's suppose you are given string source. Let's suppose you are given a destination. It is also in string. And similarly, let's suppose you are given string helper. And number of disks are given to you is n. What you have to do is, this is the function that you have to write. You have to move all those disks. You have to move all the disks from source to destination, and you have to use helper. And for that, what you have to do is you have to make use of these two rules. So the first rule is that you can keep only the smaller disk over bigger disk, and you can move only one disk at a time. And what you have to do is you have to print instructions of movement. You have to print movement instructions. You have to print movement instructions, right? So this is the expectation, right? So I have to fill this function. This is the expectation. This is my problem. Expectation is pretty clear. Expectation is that I have to fill this function. But what about faith? So for clearing the faith, let's try to solve it for some functions. Let's try to solve for n equal to 1. So if n is equal to 1, and let's suppose we have these three rods. This rod is, let's suppose, A. This rod is A, this rod is B, and this rod is C. And let's suppose there is only one disk, and let's number it 1. So what would be the instructions? What would be the printed instructions? So the printed instruction would be that move disk 1 from A to B, right? So this is my destination, and this is my source, and this is my helper. So there is one instruction. There is only one instruction to be printed, right? So I would directly put it up from here, and I'll directly put it over here. So this will complete my answer, right? So for n equal to 1, it was pretty simple. Now let's try to solve it for n equal to 2. So if n equal to 2, let's try to solve it for n equal to 2. So for n equal to 2, let's suppose you have these two disks. So what you will do, let's try to solve for n equal to 2. So first what you will do is you will move the first disk from A to C. You would move the first disk from A to C. Then what you would do is, since the first disk is moved from here to here, then you would move the second disk from A to B. Move second disk from A to B. Move the second disk from A to B. So move this from here. So now the second has moved over here. Then what you can do is you can take this disk and put over here. So now you can put this disk from C to D. Now the question looks complete. So if n is equal to 2, this is my instruction. These are my instructions. And if n is equal to 1, my instructions would be equal to that move the first disk from A to B directly. Move the first disk from A to B directly. I'm trying to find the faith. I'm just dry running it for a small cases, right? Now let's try to solve it for n equal to 3 as well. If n is equal to 3, let's try to write the instructions over here, and let's try to do the animations over here. So let's say that A is my source, B is my destination, and C is my helper. So these are my disks. So this is A, this is B, and this is C. So what I need to do is I would first move my first disk from C to A. So this moves over here. Then what I should do is not like that. Okay, this would not give my answer. So let's first move C to B. So let's first move C to B. So let's first move C to B. Okay, a little mistake that I have done is, let's name these disks as 1, 2, and 3. So first what we should do is we should move 1. Okay, let's name it as 3. So first let's move 3 from here to here. Then let's move 2. Now let's move 2. So let's move 2 from here to here. Okay. Then what we should do is, I have moved this from A to C. Then I think what I should do is I should move this disk from here to here. I should move this disk from here to here. So then I should move the third disk from B to C. After this, I think that now my plan is quite clear. Now my plan is quite clear. And now what I should do is I can directly put my first disk from source to destination. So I should move my biggest disk from A to B. So let's move from A to B. So if I move it from A to B, so this would move from here to here, right? So now my biggest disk is over here. So now what I should do is, now it looks pretty simple. Now I'll take the third disk from here to here, then I'll put the second disk over here, and then I'll put the third disk over here, right? So let me do that. So let's take A from C, 3 from C to A. Then let's take 2 from C to B. And then let's take 3 again from A to B. Now let's try to apply this over here. So this would be removed from here like this. Let's apply here. So see, third disk would be moved from C to A. So third disk would come over here. Then the second disk would be moved from C to B. So this would be moved over here. Then I'll move this disk from here to here. So this would be my third disk. So these are the steps, right? I have got it. I've got it. So these are the steps. These are the steps which would be applied to move all the 3 disks from A to B, from source to destination, right? So what I think is that now it's time to see my faith. Let me try to journalize these things. Okay, so right now what we are doing is we are seeing these 3 steps. We are seeing these 3 steps, the above 3 steps, these 3 steps as individual steps. So, but we can see them combined also. In these 3 steps, what I have done is, in the earlier 3 steps, what I have done is, I have moved these smaller 2 disks. There were 3 disks, one was 1, other was 2, and other was 3. I have taken the above 2 disks, I've taken the n-1 disks, and I moved them from A to C. Can you see it over here? Can you see it over here? So in the first step, what I could write is, I can say that move the first 2 disks, move the above 2 disks, and move them from A to C, move them from source to helper. Move them from source to helper. Then I can say that now my destination is completely free. My source has only 1 disk, which is the nth disk. Now you can move the nth disk from source to destination. And after that, try to see these 3 things. Try to see these 3 lines. In these 3 lines, what I have done, I have moved my all the disks, my n-1 disk from helper to destination, from C to B. So I can say that I have 2 faiths. My faith 1 is that I have to move n-1 disks from source to helper using destination. Then I have to do some work. So I would move the nth disk from source to destination. Then my fate 2 would be equal to that I have to move my n-1 disk from helper to destination using source. I think I would have 2 fates. I think I would have 2 fates. So the step 1, as Bhagya Rana is saying in the comment section, that move n-1 disk from source to helper. And then what you would do is that you would move, then you would move the biggest disk from source to destination, right? And then what you would do is, in the next step, you would take all the n-1 disks which you have kept at helper, and then you would move to the destination. Step 2 would be the nth disk to destination, and then the step 3 would be take n-1 disk from helper to destination. So these are the 3 things, right? So if I could take you to the code, right? If I could take you to the code, so this is the code and this is written in Java. So in this code, what I've done is, I have written faith 1. So my faith is that I would take the disk, n-1 disk, and I'll take from the source and I'll put it in helper using destination. So my expectation was that you have to print the instructions of moving source and disk from source, and you have to put it into destination using helper. My faith was that I have to take n-1 disks from the source and I have to put it into helper using destination. Then I'll do one thing on my own. I'll take the nth disk and I'll move from source to destination. After that, I'll take n-1 disks from helper and then I'll move it to source. Then I'll move it to not source. This should be destination. This should be destination. This is a little wrong and now it is very correct, right? So this will complete and this will take all the disks from source to destination, right? This is in Java, but I think you get the proper gist of it, right? I use Java because I wanted to explain everything. I wanted to dry run and I wanted to debug. But since we don't have the time to debug, you have to understand that, that how debug is done, how dry run is done. I'll move quickly to that part in a minute. Let me just quickly run it and let me show the output of this question. So first, the first disk would be moved from A to B, then from A to C, and then from B to C. Then the third disk would be moved from A to B, and then first disk from C to A, then second from C to B, and the first disk from A to B. So first we are moving from A to C. We are moving first disk and the second disk from A to C. Then we are making the biggest movement from A to B. Then we are again making the movement from C to B. This is what you have to realize in recursion. You have to realize these things. For somebody who's asking what this IDE is, what this integrated development environment is, this is Eclipse. And Eclipse is generally used to run problems, execute programs which are written in Java, right? Right. So this is how things are, right? Now let me quickly try and dry run this. So to answer Bhagya Rana's question, that what is the step after transferring nth disk from source to destination? So this is step 1, this is step 2. Bhavya, the step 3 would be take n-1 disk from the helper and put it into destination. Take the n-1 disk which you have kept at helper, put it into destination, and then you have to use the empty source rod. Move the n-1 disks which are in helper and move it in to the destination, right? So this was all about this webinar. And if I could quickly tell you how this is being done and how you would dry run everything. So Tower of Hanoi. So this is how you dry run. This is A, then B and C. I'm talking about these things. So this is how you dry run it. This is the code which is given to you. So this is how you dry run. Tower of Hanoi is given to us, source name is given to us, and destination's name is given to us, then helper's name is given to us, and then n equal to 3 is given to us. Then make the first call. First line gets executed, the first call, you have to see what happens in first call. Source gets replaced by source, destination gets replaced by helper, helper gets replaced by destination, n gets replaced by n-1. So the first call would be A, C, B, and 2. So, and after that, you will come over here. The first would get executed, and you will run everything over here. A big tree would would come over here. But this is how things have to be done. I'm not dry running it to that extent. I would come back from here, and then I would execute this line. I would come back from here, I would execute this line. This would print in the console. Then I would go to the third step and I'll move and I will make another call. So when I make another call, source is replaced by helper, destination is replaced by destination, helper is replaced by source, and n is replaced by n-1. So this would be replaced by C, this would be replaced by B, and this replaced by A, and this would be replaced by 2. So for dry running this part, you have to execute this to the much greater extent. You have to dry run this to a much greater extent. But since we don't have that much amount of time, we're running out of time, so I cannot execute or dry run it to that much extent. I would just request you to dry run everything and execute it and try to apply all the insights that we have applied or we've learned so far in Tower of Hanoi. This is something which will be useful for you in trees question as well. So somebody earlier in the comment section asked me how trees question can be solved. So this question, which I have just solved, this Tower of Hanoi, this can be solved. This gives you an intuition. This gives you a way how trees question has to be solved. Here what I have done is I have just made one call and I have assumed that this call would do everything correct. This is my faith one. Then I have done my work. Then I have made another call, my faith 2, right? So you have to solve trees question like this only. You have to have faith on the left node, and you have to assume that the work that you want to do for the left node, that recursive call would do everything on the left node. After the call comes back from the left node, then make a call to the right node, right? The dry run that you would do for the Tower of Hanoi would give you valuable insights for the trees question as well. So I would request you, see how things are going, see how function gets executed, see how whole dry run gets over, see how everything goes, and try to build insights from it. And if I could give you more insights on how you can take your learning further. So after doing Tower of Hanoi, you should learn that how recursion questions are done in data structures. Like let's talk about arrays, or let's talk about strings. And let's talk about something called 2D arrays, right? So after learning this much amount of work, after getting to know how recursion works, you should understand how arrays, strings, and 2D arrays work, and how recursion works in combination of recursion in arrays, how it works in combination with recursion with string, how it works, recursion with 2D arrays, how these combination works, right? So for that, first thing you should do is how arrays behave in stack frame, how string behaves in stack frame, how 2D arrays work in recursion in stack frame. After that, you can solve questions on recursion. I would like to give you some questions, like you can print some subsequences. There are two variations to solve it. One is get variation, another is print variation. You are given a string ABC, try to print all the subsequences using a string. For arrays, you can check if a given element is present or not in arrays. For 2D arrays, you can solve questions like flood fill algorithm. Try to solve flood fill first. Then you can move to better questions like n queens, or you can move to Sudoku, or you can move to crossword. First, try to understand flood fill. Flood fill is one such question whose insights will help you in a lot of questions. So try to learn all those things, apply in all those things, and probably you will be able to get into recursion. So that was all from my side. I hope I was able to help you. And what I would do is I would basically give you everything that we have learned so far. We will share notes of that, right? And flood fill, somebody is asking what is flood fill? Flood fill is an algorithm. Flood fill is an algorithm. Do some Google and try to learn flood fill algorithms. It's an application of recursion with 2D arrays. And this get and print variation, which I'm talking about, this is recursion with strings. So try to solve these things. Now try to learn recursion with data structures, right? After 2D arrays, you can move to recursion with linked list. After that, you can move to recursion with stacks and queues. Then you can move to recursion with trees. You have to learn how they behave in the stack frame. That's the most important thing, right? Okay, so I think that was all from my side. I would obviously share some notes with you, and I would basically share some notes so that you can optimize and learn and see whatever we have learned. You should have something, because you cannot go in the whole webinar again and see everything. You want to revise something. So what I will do is I'll share notes. You can quickly go through the notes and you can quickly get everything detailed in a detailed manner. It would be written on those notes, right? From everything starting from PMI, from then moving to sum of n natural numbers, then print decreasing, increasing, then factorial, power, and at the end, the most important, tower of Hanoi, right? And apart from that, if anybody of you wants to connect with me after this webinar, I would basically would be very happy to answer your questions. And you can connect with me on navdeep@codingninjas.com, right? Sure, sure. We will basically share the notes in the description section, right? Okay, okay, okay. So thank you very much, guys. Thank you, thank you. That was all from my side. Thank you.